So we're going to make use of a p-n junction, and we'll talk about all the different, well, a lot of different types of diodes. There's probably a few others that aren't on the list. Um, so for a general purpose diode, it's just a p-n junction, nothing special about it. Um, you have to forward bias it, in other words, overcome that barrier voltage in order for it to conduct. And it only conducts in the forward direction normally. If you apply a reverse voltage at a certain point, it will avalanche and conduct in the reverse direction. It's called the Zener effect. And we'll talk about that probably as the next diode. Um, let's see. Yeah, it doesn't normally conduct when it's reverse biased unless you get up to a high enough reverse voltage. When you apply a reverse voltage, okay, what in effect is happening is that depletion zone we talked about gets wider. So remember, we have, even though they're not conductors, we have a positive and negative potential on each side of that depletion zone, which means if there's a positive charge here and negative charge there, what's in between? An electric field. If we have an electric field, it's storing electrostatic energy, and we call that what? A capacitor. So as we vary the negative voltage, and I'm getting ahead, we vary the width of the depletion zone and we vary the capacitance. That's how we make a varactor. So they figured out a lot of things, the way stuff works, and they took advantage of that effect. And of course, they construct it differently than a regular diode to enhance that depletion zone characteristic. So your normal semiconductor general purpose diode is just a piece of P material, N material. It automatically creates this depletion zone, depletion region. Sometimes they call it a layer. We represent it with the symbol of this filled in, usually a filled in triangle as the anode, indicating positive current flow, because Benjamin Franklin said that's the way current flows. Well, 50-50, he didn't know any better. And then the straight bar is the cathode. And that's on a lot of diodes, probably most, that's how they're marked. They have a stripe, which indicates that's the cathode end. And like we talked before, if it's germanium, that barrier voltage is approximately 0.3 volts. If it's silicon, it's approximately 0.7. It's actually a little curve, so it depends on where you measure it. Kind of we talked about that on how the depletion region is formed, and you get the electric field across that region. So that's what generates that voltage potential. Here's typical diagrams for a standard diode. A Zener diode kind of has the little Z as the cathode. A Schottky diode we'll talk about looks like an S for Dr. Schottky. A varactor diode to make it look like a capacitor because it's a voltage controlled capacitor. We're not going to talk about tunnel diodes. They have this little sort of represents a tunnel, I guess. Light emitting diodes and photodiodes. They can actually be the same, but light emitting diodes are optimized for different color lights. It turns out all diodes, all p-n junctions emit light. As an electron crosses the barrier, okay, it has to be up to a certain energy level to get there. when it gets across the barrier and recombines, it releases that energy. And that energy is dispersed as heat and light and electromagnetic. So normally diodes and transistors are in opaque packages. You can't see it. But in the case of light emitting diodes, they took advantage of that. So they put them in a clear package so you can see the light, and then they do things to enhance the amount, to amplify the amount of light that's emitted. Okay.
Are you saying that if diodes were housed in clear plastic,
Yes,
that they would light up?
they would emit light. Now, the frequency you may not be able to see because the amount of potential difference, the amount of energy released determines the frequency. That's one of the things that how you change the frequency for LEDs is they play games to control the amount, the barrier, and that will determine the wavelength of light released. But all PN junctions actually emit light at some wavelength. They will also accept light. So light coming in can actually cause current to flow. We call that a photodiode or a phototransistor. Doesn't matter where the PN junction is. What's the approximate forward threshold voltage or barrier voltage of a germanium diode? What's the approximate forward threshold voltage of a silicon junction diode? How does a PN junction diode not conduct current when reversed biased? Why does it not when reverse biased?
Charlie.
Well, I'll give you a hint. It's not Alpha or Bravo. Charlie. Yeah, I guess when you apply that, I mentioned when you apply a reverse voltage, okay, it widens the depletion region, and the width of the depletion region determines that barrier voltage. So the barrier voltage gets much larger when you're reverse biasing it. So a Zener diode takes into account the effect that when it's reverse biased at a certain voltage, it will avalanche over. I think the guy that discovered that was named Zener. I'm not sure, but it's called the Zener effect. And they can manufacture diodes where they control that Zener voltage precisely, so you can use them as a voltage reference. And in fact, it's very common to see it in a voltage regulator circuit as the reference voltage. There's a plot of the current, and you can see in the positive direction, you have a little bit of leakage current until it gets up to the barrier potential, and then it's only limited by internal resistance. When you go in the negative direction, it's going to have very little leakage current. It will have some in a real diode until you get to the Zener voltage, and then it avalanches. And again, it's only current is limited by the internal resistance of the device. In the theoretical diode, these would be vertical lines. They'd have no internal resistance. And we use that little Z to distinguish it from a regular diode. So what's the most useful characteristic of a Zener diode? Bravo. The voltage is almost constant, regardless of the current. Varactor diodes. So we're going to take advantage of the depletion region and use it as a capacitor. So we reverse bias it, and the amount of reverse voltage is going to control the width of the depletion region and therefore the amount of capacitance that it will appear to be a capacitor and store energy. So it becomes a voltage controlled capacitor. And that's probably how all modern radios tuning capacitors are varactors. No more turning a knob with plates. You're turning an encoder that's changing the voltage. They actually make them special to enhance that capability. And they have this metal contact. You got your p-n junction. I don't know what the epitaxial layer does for it, but you can, in this thing over here, they're showing how the white, which is the depletion zone, varies depending on the voltage. So the wider the depletion zone, the lower the capacitance because you're separating the charges. So what type of semiconductor device is designed for use as a voltage controlled capacitor? Alpha sound good? A pin diode. They use these as essentially voltage controlled resistors in usually RF and microwave circuits. So, and you can also use it as a switch. A lot of times they will use pin diodes on each end of a filter circuit so that you can switch bandpass or low pass filters in by controlling the voltage on the pin diodes that make them act like switches. They either conduct or they don't conduct. It's much quieter than using relays to do that. So if your auto tuner makes a lot of noise, it's got relays. If it's quiet, it may have pin diodes.
These similar to a MOSFET, using a MOSFET as a switch.
Well, I guess you could, but it's a lot simpler to use a diode and bias it. And you can actually get the same effect with a like a 1N407. That's kind of a typical power diode, handles a few amps. They will act like a cheap pin diode, not as well, but they're a lot cheaper. It has one of the advantages is very low junction capacitance, where the MOSFET, you're going to have more capacitance. So these you can actually use also as a variable resistance as opposed to just switching it on and off. You can either get zero or high resistance or something in between that 0.1 and 10K. It's represented with kind of the line going through it. I'm not sure why, but this is the one that uses intrinsic silicon between the P and N layers.
Now that's pure silicon.
Pure silicon, unadulterated, undoped silicon. What characteristic of a pin diode makes it useful as an RF switch? Low capacitance. Because at high frequencies, if you have capacitance, you've got conductance. What is used to control the attenuation of RF signals by a pin diode? Alpha. Alpha sounds good. A Schottky diode named after Dr. Schottky. A lot of times they call them hot carrier diodes or a Schottky barrier because the barrier voltage is less. And that's its main advantage. So they started using that technique in integrated circuits. And there was the Schottky series or the S series of like the 7400 integrated circuits. And then they came out with low power Schottky or LS versions. They were because they had low capacitance and a low barrier, they were very fast. So they could use up in the multi megahertz range. And sometimes you'll use those as mixers or detectors in VHF and UHF because of that low voltage drop. So the way you make it is a p-n junction, or excuse me, an n junction and metal as opposed to a p. So the metal is going to supply the receptors, and the n-type is going to supply the free electrons. Exactly how it works, I don't know. It winds up with a very small barrier or depletion zone, which is why your forward bias voltage is much lower because of that.
And fast.
And faster because less, well, it actually had a little more, ought to have a little more capacitance, but depending on the area, you see over here the way they make it. So you have a very small area. So the area of the plates is one of the factors in capacitance. So not only the separation, but the area. So smaller area lowers the capacitance. Exactly how that works between the n-type and the metal, I'm not sure. Like I said, we represent it with this kind of S symbol for the cathode. They're still marked the same way with a stripe. So you have to know it's a Zener diode as opposed to a regular diode by its part number. It's not going to say Zener on it.
I noticed that the stripe on the drawing there of the resistor is on the end, and the regular diode, it was more toward the middle of the diode. Does that make a difference?
No, it's towards one end, doesn't have to be exactly on the end.
Okay.
But yeah, you said resistor, this is a diode.
Did I say resistor?
Yeah, you did.
What I meant was-
You said Zener, you're gonna shock me.
Yeah, well, I'm old. How old are you?
What is this, February, March?
Yeah.
Yeah, I'm still 75.
Oh, hell, you're young.
What?
I'm 81.
No way.
You're 81.
Yeah.
Wow.
Oh, shit.
That's why I forget things.
Pretty well.
Well, see, that's the worst part. If you remember that you forgot something, you fret about it. At a certain point where you don't remember that you forgot, it's cool.
Yeah, it's gone.
Which characteristic of a Schottky diode makes it a better choice than a silicon junction diode for use as a power supply rectifier? D, lower forward voltage drop. Because when you,
The other is not a lot of power supplies.
Really?
yeah.
Yeah.
I mean, that's wasted power, across that junction and voltage. Which of the following is a common use of a Schottky diode?
It's a detector. Oh,
We hadn't talked about negative resistance things.
That's all we negative resistance,
Huh?
negative resistance, and move. Well, there's.
Well, that's what you get switching power supply.
Yeah.
Which of the following is a common use of a Schottky diode as a mixer or detector at high frequency? When you do a balanced mixer out of diodes, you want as low a voltage drop across them as you can get. Which of the following is a Schottky barrier diode?
Bob, the screen I'm still seeing question at Echo 6 Baker 02 in the top left. Have you changed the screen you're on?
Yeah, I'm on Echo 6 Baker 8.
Strange. I'm still
On
seeing you move
6?
around, but the screen share is still stuck on the previous picture or question.
Really?
Is it that way for anybody else online, or is it just me?
You're on which one, 2?
I'm seeing number 2. Yes, sir. John, I saw you on mute. What were you seeing?
Yeah, I see two as well.
So it's like your screen share kind of got frozen, but your local apparently is updating.
Yeah, it's changing here.
Just stop sharing and reshare.
Yeah, something happened up there that blocked it. It was normally green and it turned red.
All right.
Yeah, we complained about Spectrum a lot too, and my wife convinced me to cancel the Spectrum and let's get the T-Mobile internet, and I wish I had stuck with Spectrum loud equality.
All right. Which one were we on?
T-Mobile. T-Mobile router here. Yeah. Yeah, ours, I might not know how bad the T-Mobile internet is at my house if it weren't for the fact that every time the network goes down, my alarm notifies me that I'm unprotected. Oh, yeah.
All right. Sherrod, what do you got now?
Echo 6 Baker 06.
Okay. I don't know what that was. All right.
It's weird. I've never seen Zoom do that. Thank you for updating that. Appreciate it.
Okay. So what's the common use of a Schottky diode? Still Delta. Well, he didn't see it.
Slide feed froze.
Which of the following is a Schottky barrier diode? Alpha.
Yeah.
Are you still good, Sherrod?
Yes, sir. It's rotating right along like it had been. Appreciate it.
Okay. Point contact diodes or cat whiskers. It's kind of a normal p-n junction, except they use this little tungsten wire, or I guess sometimes phosphor bronze, to make contact with it. I'm not exactly sure what that does. And they also typically make them out of germanium. So because of that wire contact area, you get very low junction capacitance, although I thought that had to do with the area between the P and the N, but it looks like they're minimizing that also. I'm not sure. But usually you use that for an RF detector because of the low capacitance and the fact that with germanium, it's got the 0.3 volts instead of 0.7 volts. So what's a common use for a point contact diode?
Detector.
Okay, light emitting diodes. Like I said, it turns out all p-n junctions will actually release light. or accept light. So normally when you put a forward bias voltage on the LED that's high enough to overcome the barrier voltage, it will conduct current and it'll emit light. And it's because it's in a package that allows the light to be transmitted. It's some transparent plastic, usually. You see the light. And it can be all different colors. They make everything from white to everything in between to blue, or also infrared. They may even do ultraviolet. I'm not sure. I wouldn't doubt it. The symbol is basically the same except for a couple little arrows showing light coming out. And it's made kind of the same way with your p-n junction. And because it takes energy to get those electrons to cross the barrier, when they get across and recombine, and that's what this bottom chart is trying to show. It's a little confusing. But when they recombine, they lose that energy. So it has to go somewhere, it gets dissipated. So depending on the amount of that energy, what that band gap was, will determine the frequency of the light that's emitted, and also how much of it is, it's split between phonons and photons. Phonons and photons. A phonon is a low frequency vibration, mechanical type energy. Photons are light or electromagnetic, because light is just one spectrum of electromagnetic radiation. Just like our radio waves are electromagnetic, just much lower frequency than light. So what property of an LED semiconductor material determines its forward voltage drop? And wait for Ed. Band gap. Amount of energy it takes to get across the barrier. And typically you're going to see bias voltages or barrier voltages in the volts when you look at an LED. Much higher. And they're all going to be different. Colors are going to be different because of that. That's how you get to different wavelengths. Plus special coatings that sort of phosphoresce or something and help change the colors a little bit. And so here we have a figure E62 with a bunch of diode symbols. So what's the schematic for a Schottky diode? Okay. Junction temperature. I forgot to get rid of the white. So in all cases, the junction temperature of the device, whether it's actually a diode or a transistor, is something you have to watch out for. So if you've got a high power, high current device, normally it would have some kind of a heat sink or something to keep the temperature down, because you got to maintain the junction temperature below a certain value or this thermal runaway and fails. Whether it's a diode or a transistor, it's the same problem.
It's the smoke escape.
The smoke escapes, yeah. Well, they don't always smoke, they just don't work. Although I've had them pop. What causes a junction diode to fail from excessive current? Yep. Display devices. So what is a display device? The long definition, it's an electronic device whose main purpose is an interface to show the reading or information as a result of a certain process of a computer or electronic circuit.
Wow.
Need to memorize that one.
Yeah.
buddy.
Basically, it indicates something. So typically nowadays we have light emitting diodes that are used to indicate things are on and off, use the colors to represent stuff, turn the red one on if you get some kind of error, green one on if things are cool. Also liquid crystal displays are in most modern radios, be it a handy talkie or a base station. Normally they have an LCD display. It may be color, may be monochrome. And it can use either ambient light or backlight, depending on the LCD array. If it uses ambient light as a reflective one, they tend to work better out in the sunshine because you get contrast. The backlight doesn't work too good in the sun. How is an LED biased when emitting light? Forward biased. Okay, so we covered all the diodes we care about.